Hi, welcome to Clodicast. My name is Ajay Clody. This podcast aims to understand history, science, and politics with the help of experts. Today, we're joined with renowned seismologist Adam Pascale. Adam works with the Seismology Research Center located in Australia. Today, we're going to be exploring earthquakes, seismology, and what to do if you're trapped in an earthquake. Hope you enjoy. Hi, Adam. Welcome to the show. Starting off, I'd like to ask, who is Adam Pascale and why seismology?
It's not the career I planned. I started working at the Seismology Research Center after I graduated university. I studied computer science at what was Phillip Institute of Technology back then and became RMIT University. And then at the end of that course, I didn't really have a path forward. So I just got a summer job in the basement of the building at the university where this weird little earthquake lab was. And yeah, I've been there ever since. So that was 30 years ago.
That's interesting. Knowing little about seismology, I would assume you'd do something like physics or geology before venturing into seismology.
I studied computer science, and there was an instrumentation stream, which sort of basically means computer control of instruments. And in the end, that's where I've ended up. I've gotten into designing the seismic instruments, so seismographs and software. So having that background in computer science has actually, come
Beneficial.
useful. Yeah, so a lot of our staff don't have traditional geological backgrounds. Some do, obviously, but we've got a mix of people working for us.
From then to now, what do you think makes you get up in the morning? What motivates you on a daily basis to pursue seismology?
For a long time, it was just a job. I was processing data and doing field work, and eventually I found that I really took a lot of joy from getting involved with the design of instruments and making them, user-friendly and that sort of thing. So designing is really a passion now, and I'm fortunate to be in a position where I can choose to do that within my job in developing new instruments and new software for analysing earthquake data. That's a really high motivation for me to keep involved. Obviously, earthquakes are interesting when they happen, and this week's been pretty cool. That's my motivation.
And I have to ask, what did you think of the most recent earthquake in Melbourne, Australia?
Pretty much standing exactly where I am now, and on the upper floor of our home, and that tends to amplify the shaking as well when you're further up in a building. So yeah, it started shaking. I knew immediately that it was an earthquake, and I started counting the number of seconds until the strong shaking starts, which gives an indication of how far away the earthquake was. So yeah, pretty quickly, I had an idea of roughly how far away the earthquake was, and I assumed, given that distance, it was going to be another Maui earthquake like we had in 2012 that was also felt all across Melbourne. But within a couple of minutes, I'd gotten onto the computer and worked out exactly where it was and how big it was, and yeah, it's pretty incredible.
Now, you work at the Seismology Research Center. Can you briefly explain what are the goals and aims of the center and what you do there?
So when I joined, as I mentioned, it was part of RMIT University.
Right.
And in 1998, the university sold us to a private organisation where we continued doing what we were doing, which was traditional earthquake observatory operations, so running a network of seismographs, but also doing earthquake hazard evaluations, which is basically looking at a particular site and seeing what the chance of an earthquake is for that area for design purposes, like for dams and other structures. So we were doing that within the university, and then once we were commercialized, it sort of a little bit more focus on the instrumentation side of things came about. So we started to really do more in our development work in that area. And that's, yes, the three divisions of what we do now really are the earthquake network operation. So we have about 50 stations in our network that are sending us data throughout Southeast Australia. So that's one part. The other part is that earthquake hazard evaluation, that consulting work that we do. And the other side is the instrument and software design and manufacturing. So we do that here in Melbourne.
Can you please expand for us? What do private and government organizations, what value do they derive from seismology services, especially from the research center?
Mainly from emergency response. They've got emergency procedures that they need to follow after certain types of events, after fires or other emergencies. So earthquake is one aspect of that. So they have an emergency plan that they need to enact. And most of these, the customers that use our services for an earthquake alarm service have large infrastructure that is vulnerable to earthquakes. So they need to know pretty quickly, how it affected their structure. Not so much how big the earthquake was and where it was. That's interesting and it goes along with it, but really how it affects their assets. And often they will have lots of assets that need to be evaluated. So they all have limited resources to be able to do that. So they need that prioritized as quickly as they can. So we work with them before an earthquake happens to say, these are where your assets are. These are what their relative vulnerabilities are. So if there was an earthquake of this size at this place, then that means this asset needs to be looked at first, and then this one and this one and this one. Now, in the case this week, it was such a large earthquake, everyone felt it, and they basically just jump into action straight away to get all of their major assets inspected as quickly as they can. But it's in when you have smaller events, which can be felt widely, but actually only really affecting, a few of their assets, they won't know where to send the people their resources. So that's what we do. We try to help them focus their emergency response and give them exactly what they need, not just the latitude, longitude, depth, and magnitude. It's this asset would have received this sort of intensity of shaking, so you need to take the action plans related to that. So we try and do that within a couple of minutes of the earthquake happening.
I know seismologists they don't have a structured routine. Can you paint us a picture of what you do on a daily or weekly basis to get a better understanding of what seismologist does?
There's certain aspects of what we do are routine. So on a weekly basis, we're processing data from all of our stations that we're getting data from. So there's data streaming in from, as I said, dozens and dozens of stations. So we've got majorly one data analyst going through most of it with a couple of backups as well. We're locating every earthquake that we can see. And because generally in Southeast Australia, we don't have very many large events, we are often looking for very, very small events. And we have high density networks, so we can pick up very, very small earthquakes, less than magnitude 1, less than magnitude 0 in some cases. So because it's a logarithmic scale, but we can talk about that later if you want to get into that. So we're locating those earthquakes, and then we're producing a weekly map that we put on our social media. So we've got Instagram, Facebook, Twitter, and LinkedIn. We've put out maps every week of earthquake activity. Monday's one's going to be pretty intense compared to most weeks. This week we're going to have hundreds and hundreds. So that's the routine part of our earthquake operations. The other parts, we're constantly developing new software and hardware. So we're on our 7th generation of recording instrument. The data logger that we develop is a seismograph. A seismograph is a data logger combined with an earthquake sensor. So we don't make the sensors ourselves. We design our own data loggers. So that's important because seismic data loggers are not like most other ones. They need to have a very wide dynamic range. They can pick up very small and very large things. They need to run very quickly, hundreds of samples per second, rather than just logging, one sample every minute or 15 minutes like some other data loggers do. So it's a very specialized sort of thing, which is why we started developing these ourselves back in the late 70s. So yeah, we're on our 7th generation. We're working, that's in production at the moment, and we're developing our 8th generation at the moment. And we also develop software to go along with it. So data analysis software to, be able to actually locate the earthquake, to host the data, to pull it all in, and to be able to access it over the web.
Okay, now we've covered a bit about seismology and what a seismologist does. Can we delve into briefly what an earthquake is in a nutshell?
So an earthquake is basically a rock breaking. So what's happening dynamically around the world, everyone I think knows nowadays about tectonic plates that make up the surface of the earth. We in Australia are within a tectonic plate. We're in the middle of the Australian plate, the border of which goes through New Zealand and then sort of bends around through Papua New Guinea and Indonesia. So that's where two plates are meeting. So the Australian plate and the Pacific plate meet together. And at those plate boundaries where two plates join, that's where you get a lot of more frequent earthquake activity and much larger earthquakes more often. So because they're sort of rubbing past each other as they're moving. So there's a lot of movement, a lot of big earthquakes more often. Within the plate itself, though, as it's being pushed around, stress is being built up within that plate. And that can sort of, as you're compressing the plate, that can cause little fractures and faults within that plate. And occasionally they will break as well. So the rock can only take a certain amount of stress, and different rocks in different areas take different amounts of stress, and then they'll break. So the stronger the rock, I guess, the more it can take. And then when it breaks more severely as well. So that's how you get different magnitude earthquakes. When that energy release is, it depends on how much stress that rock has built up. So that's the dynamics of what happens during an earthquake. That's that rock breaking. And then energy waves are released when that break happens. Now, there are two major energy waves that come out. We call them P and S waves, primary and secondary waves. Primary waves travel faster than secondary waves, but the secondary waves are the ones that tend to be of larger amplitude and shaking horizontally, which is the problem, because that's what buildings don't really like, is being shaken sideways. Yeah. They are usually primarily vertical because they're compressing as they're pushing along rather than waving as they're moving along like the S waves. So those compressional waves that happen with the P wave, so they'll arrive first, and then some number of seconds later, depending on how far away you are from the earthquake, the S waves will arrive. And we use that time difference between the P and the S wave to actually work out where the earthquakes are. It's just triangulation. Basically, if you have at least 3 stations that have recorded the earthquake, you can work out where the earthquake is in 3D space.
Similar to how police track people's cell phones between towers.
It's a range thing. So you get range from 3 different places, and then you can narrow it down to exactly where it is. And the more seismographs you have and the closer they are to the epicenter, the more accurate the location is going to be. And depth plays a huge role in that. So if you can have a seismograph very close to where the earthquake is, you get a real good idea of how deep the earthquake is. And in this week's earthquake, we had stations within 50 kilometers of where that earthquake was, because it's a fairly active area, and we know when we put things in that area, and we work out that the depth of that earthquake was 12 kilometers, which is pretty standard. Sort of 10 to 12 kilometers is not unusual for our part of the world. And that's how we determine the location and depth and magnitude of an earthquake, is basically how much shaking it generated.
Is that related to how seismologists calculate the magnitude as well, by the amount of waves?
Yeah, so the amplitude of shaking at the different distances, we then calculate basically at 100 kilometers it shook 10 millimeters per second. At this station, that was closer, it shook more. So we average, there's a formula to work out the local Richter magnitude. So everyone's heard of the Richter magnitude. It's not really used scientifically these days, but we still use it ourselves to give a relative measure of the size of these earthquakes. So we estimate the Richter magnitude using that formula for each of our seismograph stations, average it out, and then that's how we get a magnitude. So more modern methods of calculating magnitude are called moment magnitude, where they're working out fault plane areas and things like that. It's a bit more difficult to understand, but to be consistent, we try and use the same sort of rough scale. So even though this is this week's earthquake was local Richter magnitude 5.8, the moment magnitude works out to 5.9, but they're pretty similar.
Can we go over the types of equipment that seismologists use?
So the field equipment that we use is, the first part is the earthquake sensor. So this is a device that has usually 3 components in it, measuring north-south motion, east-west motion, and up-down motion. So it's a triaxial seismometer, we call it. So that produces an electrical signal, and we connect that to a data logger, which is the equipment that we develop ourselves at the Seismology Research Centre. So that data logger will collate that equipment, that data rather, and store it onto a memory card, and optionally stream that data onto the internet to our observatory. So we usually will connect it to a 4G modem nowadays, but you can also connect them to like other internet systems, satellite communication systems, whatever's available really. So it will stream that data remotely. To power those systems, you've got a battery and a solar panel, usually because they're remote. We want to have our stations as far away from noise sources and population and traffic as possible. So that usually means we don't have any power. So we're always running off battery power. So all of that equipment needs to be very low power consumption. So we make sure we design our equipment to operate that way. So that's generally what's out in the field, and that's what we put out in the field this week for some aftershock monitoring of this event as well. We had some gear sent down from Geoscience Australia in Canberra, who's the national authority for earthquakes in Australia. We went out there to install it for them because they've got travel restrictions due to COVID at the moment. So we're cooperating well and to get all this data.
Are we using any AI or machine learning technology to analyze or predict these patterns or seismic waves, or is majority of the analysis done by humans?
It's still very manual. We have never had enough activity to really justify developing that the machine learning ourselves. It is out there in the world. People are doing it. They're doing pattern matching of events. And that usually works well when you've got lots of events in the same place, like we're seeing now with all these aftershocks. It is very, very labor intensive to go through hundreds and hundreds of aftershocks and process each one. We're not usually in that situation. So I can see the real benefit of doing that at the moment, that we could just say, okay, this is what a Woods Point earthquake looks like. Go and find them all and match them up, rather than us having to locate each one. That's becoming more and more common nowadays. So there's a lot of researchers out there that are doing it. A lot of the code is open source. It's just about, how we integrate it into our software systems. And that's one of the things that we try and focus on, is all of that technology is out there, all of that code's been developed. And what we try and do is put it into a package that is really easy for researchers and students to use. And we haven't gotten to the point of integrating that machine learning stuff into it yet, but it's certainly on the cards down the track.
Now, diving a little bit into the history of earthquakes, has our understanding fundamentally changed in the last 100 years, or has it been pretty much consistent with what we know and understand earthquakes to be?
There's a lot of things have changed, and I mean, plate tectonics isn't that old an idea. Actually, people didn't really understand the way the Earth was made up for a long time. So that's really developed. In the 1960s, there was a real push for more earthquake monitoring around the world, and that was really when things started to ramp up. A lot more instrumentation was put out, and that's when we really started to learn about earthquakes, particularly in Australia. We didn't have very much in the way of seismographs until the late 50s, early 60s. And that's when we started learning about it here. The general understanding really is, the fundamentals are pretty well understood now as far as fault rupture mechanics and the different types of faults in different areas. The research that's going on nowadays is focused around looking at different areas and also looking at different ways of monitoring things and trying to understand things like slow slip events, which are things that don't, the land moving without there being earthquakes. It's like deformation of land. So look, there's a lot of research going on and we still have so much to learn. I mean, the ultimate goal is to find those pointers that are indicating that there's imminent seismic activity, but at the moment there's absolutely no way to predict earthquakes.
I know that predicting earthquakes is not possible. Do you think in the future, if we understand all of the variables and the parameters involved with the seismic waves or determining what's happening under the earth, do you think we'll be able to predict earthquakes in the future?
I think that is the key to it, in that we don't know how to monitor. We don't know the parameter that we need to monitor to be able to determine this. And one of the things is, as we were talking about earlier, there is this stress buildup in the rock. We can't measure that stress buildup. This is the issue. I mean, this is these rocks where their breaking is kilometers down below the surface. We can't get to them. We can't monitor them directly. If there was a way to monitor that stress, then we would start to be able to determine, okay, stress is increasing, and in this area that tends to release at this level, so we'd be able to work there. It's just that technology is not there. I mean, people are working on it. They're trying to work out. I've heard of things where they're measuring things in the atmosphere above known faults and seeing spikes in certain parameters before earthquakes. So yeah, that's the trick. It's really finding what's that parameter that we need to monitor that's going to give us that last piece of the puzzle to be able to put it all together. So definitely, I think that's the goal.
Moving on to the human aspect of earthquakes, the human side, do you think the last couple hundred years, due to the Industrial Revolution and humans doing a lot of activity above and under the Earth's surface, do you think we're contributing much to earthquakes, or are we not really making a dent in the grand scheme of things?
It's I mean, certainly humans contribute to seismic activity, not on a tectonic level as far as affecting the plates and how they move, but certainly on a local scale by doing things like fluid injection. We know that can induce earthquakes or trigger earthquakes. Whether whether these areas would have had earthquakes without that activity, that's it's a fair point, is that those areas wouldn't have been triggered into having those events had we not been sort of pushing stuff in or taking stuff out. So it is bringing on events, it is triggering events that may have not happened or may have happened a long time in the future. So there is an effect. Climate, not so much. I mean, all of the tectonic stuff, again, is happening kilometers below the surface of it. What we're doing up here is very superficial, and there's been many cases of particularly with fracking, about inducing events. And the trick there really is to monitor it and regulate it, and putting in instrumentation in there to say, okay, we are seeing little fractures, and fractures are required. They're trying to open up fractures in the earth to be able for the resources to be extracted or injected. And to a certain level, that's going to be okay. But once it gets out of control, that's when it needs to be stopped. And that's, so it's manageable, but there are risks, obviously.
Do you think humans in the last couple hundred years doing excavations or mining has affected the frequency rates of earthquakes, or do you think that we just have better equipment to understand what's happening and catch these earthquakes happening. That's why we're seeing a higher frequency. Can you briefly elaborate on that?
Sure. I mean, there's a lot of factors that are contributing to our improved levels of information. And I think that that's the key. Overall, earthquake activity is no different to what it's always been. I mean, it's been happening for millions of years before we got here, and it will continue to. So the overall rate of things is not really changing. What really has changed is our ability to detect them using better instrumentation, and in recent years, our ability to communicate that information to the public. So that it appears to the public there's a lot more stuff happening. There's more earthquakes, there's more tsunamis, there's more stuff happening. It's not really, it's just you're hearing about it more because we're able to communicate it more nowadays and more quickly. When I started 30 years ago, getting the word out was really difficult. Now I can just tweet and it's there and people are consuming it immediately. So I think those are the factors that give the perception that earthquakes are more frequent but they're not. They're pretty much the same rate as always. And there is you look at the rate of magnitude 1s and 2s and 3s, and it just hasn't really changed since we've started monitoring, and we suspect ever.
And just trying to understand earthquake destruction, do you believe that population density and our ability to build larger and bigger buildings, and maybe even structurally, we haven't taken account of earthquakes in general, that's causing most of our damage and destruction from earthquakes? Or do you think there's earthquakes are just naturally that dangerous?
Definitely the engineering around the structures is the biggest factor in damage from an earthquake. Most cities have been around for a long time, a lot longer than there have been building regulations that considered earthquake. And that's why we've got issues with, distant earthquakes like we had. This Melbourne one was, we're 130 odd kilometers from the epicenter, and there was damage in the city. And the reason for it is that, that there was one particular building where the masonry fell off the building, and it's because it's unreinforced masonry. It's not tied to the structure. And this was not a common thing back when those buildings were made. They didn't consider that you could have an earthquake that will shake this building and that this wall will fall away. And in those countries where they have devastating earthquakes, in Turkey and other places where the infrastructure is very, very old and hasn't been engineered at all in some cases, and that's where you've got widespread destruction and unfortunately deaths and injuries due to it. It really the effect of the earthquake doesn't kill people. It's usually the buildings and the infrastructure that comes down around it, and that's the key. It's the age of the city. Modern cities with all modern construction, they're pretty resilient, but there's not many of those, so it's always going to be an issue.
So in theory, you'd assume that we'd be able to engineer ourselves to be more earthquake resistant and to prevent destruction and damage.
Absolutely. And in Japan, we about the construction of their buildings with lightweight timber frames and in some cases paper walls, because they are lightweight, flexible. They move in earthquakes because they've had, they've engineered those to survive earthquakes because they know they've had them for thousands of years, and they engineered their structures accordingly. In Western countries, that hasn't necessarily been the case because I guess we don't have the history of seismicity in those countries. So even in places like in New Zealand, we had the Christchurch earthquake and it was devastating. And again, it was the engineering of that infrastructure. When they were built, they didn't consider earthquake, but there's a lot of retrofitting going on in that country, particularly in Wellington, where they know that there's potential for very large earthquakes, that they go and retrofit base isolation things, like basically putting the building on shock absorbers. And you can do that to protect these heritage buildings that can't be changed in themselves to be more earthquake resistant, trying to isolate them from the ground motion. Whereas new buildings, you can actually make the frames so that they are they can twist and be flexible, but also rigid enough to survive an earthquake. So it's all about engineering.
Taking it outside of Earth, do seismic activity or earthquakes happen outside of Earth in other planetary bodies?
Absolutely. So the first place that seismometers were placed outside of Earth was the Moon. So we have recorded moonquakes since the 60s, and recently they've just last year the first Marsquakes were detected. So a special deployment was made. InSight was the lander, and that had a seismometer on it. So it was the first seismograph on Mars, and it has recorded. So the idea of putting a seismometer on Mars, not just to record Marsquakes, but to understand the structure of the internals of Mars, which is what we have learnt. All that we know about the internal structure of Earth has come from monitoring earthquakes. We look at how energy waves travel through the Earth, and that's how we've gotten that picture of what's happening inside the Earth. And that's what we're trying to do in Mars. And there's only the one station there now, but in future, obviously more stations, and you'll get a better idea of what the structure is and the dynamics of that planet. And there are plans to deploy seismographs to other planets. To Titan, I believe, is one of the future targets. All very exciting.
All right, question on everybody's mind: what to do if you are stuck in an earthquake?
There's a lot of old myths, and we just really need to put those to bed. I'll tell you the thing that we say now, there's a phrase of drop, cover, and hold on. And the idea is to get down, get underneath something solid like a table, and hold on, because the strong shaking can actually move that table. So it might move from above you. So you want to hold on to it while there's strong shaking. And the reason that we're just taking cover is because most injuries and deaths are caused by falling debris during an earthquake. As we're talking about, it's the buildings that are killing people. So you need to protect yourself from that. Now, in some cases, if you're in a building that will collapse, there's no sort of avoiding it. But getting into a position where you can protect yourself is important. Running out of the building is not a good idea. That is the instinct. People were doing that. The issue is, we touched on earlier, was that you've got walls that can fall out into the street. So you can run out onto the street, and then you can have bits of the building falling on top of you. Whereas if you stayed inside, you'd be fine. There's that traditional idea that getting into a doorway is going to help. I think that's a bit of a myth, because I think there was a photo at one point of a doorway being left of an earthquake affected building. So somebody said, oh, well, doorways are strong, so we should go and stand indoors. It's not a good place to be. But yeah, drop, cover, and hold on.
If you're out in an open field, are there any risks from earthquakes?
Generally, it's an open field is a good place to be, because you're clear of any dangers. Very rarely does the Earth open up, and so there's that trope that is not really. It's a very Hollywood sort of thing to do.
I've seen a lot of videos where if you're driving a car and you're on a bridge and then the bridge collapses, what would you recommend for somebody who's driving in that situation and they experience an earthquake?
Recommendation is to pull over and stop, because you don't know what's going to happen with that bridge, and you can't see if the bridge has collapsed if you're driving along. So if a section of the bridge is gone, you can't stop quickly enough. So the recommendation is that if you are noticing an earthquake while you're driving, which is actually quite difficult often, to just stop the vehicle and stay where you are.
Stay in the vehicle or get out of the vehicle?
Inside the vehicle. Again, it's affording you some protection. If there is some structures of that, of wherever you are going to collapse, then you've got a better chance of being protected while you're in your vehicle.
Final question. What advice would you give to people who are interested in seismology, the younger generation? Where can they learn more?
Yeah, there's no seismology courses in Australia at the moment. the nearest sort of things are in geology and engineering, civil engineering, those sorts of things, sort of understanding the dynamics of the earth and structures. Getting into, that's where a lot of people are working at the moment and studying in universities. So, obviously physics and maths play a big part in what we do. So if you're studying those areas, that's very important. But there's a lot of aspects of what we do. I mean, as we said at the start, I came from a computer science background doing programming, and there's aspects of a lot of different disciplines within seismology. For what I do, I do art and video production and lots of other things. So you can find a niche of what you want to do. But really, the important thing is to, if you're really interested in doing something, spend some extra time teaching yourself some of those aspects outside of your normal sort of study thing. Don't necessarily just rely on what's being taught to you to give you the full picture. Do your own investigation, do your citizen science, and be passionate about it, and keep working towards it, and you'll get there.
Lastly, where can we find out more about Adam Pascale and the Seismology Research Center?
src.com.au. During the earthquake, that tends to go down because everyone tries to get it, which is why we've also moved to social media to get the word out during events. There's links to all of our social media on our website. So there's Facebook, Instagram, and Twitter and LinkedIn and whatnot. And YouTube, we have a YouTube channel where we occasionally put out a bit of information. So yeah, src.com.au is the place to go. I think that's probably the best central resource for it. Yeah.
Well, Adam, thank you so much for today. Thank you for taking time out to entertain me and our audience as well. Hopefully we'll see you in the next earthquake.
My pleasure.
Hi, before you leave, if you have any ideas to explore or people to speak to, please reach out to me at Ajay Kladi on Twitter or at KladiCast on YouTube. Hope to see you in the next podcast.